I'm going to talk about Nickelate superconductors, a renaissance of the one-band Hubbard model. And for all those of you that like to study the Hubbard model, you now have the perfect justification, the perfect material to justify why you are doing it. Even much more so than the cuprates, the Nickelates can be described by a one-band Hubbard model plus an effective path for electrons that is not coupling to the Hubbard model, as I will describe later in my talk. The work I will present is a big team effort. Many people have been involved, and let me of all of them just pick out two, namely Liang Xi and Motoharu Kitatani, who did most of the work I'm going to present. As you all know, 2 years ago, there was a great breakthrough in condensed matter physics. Danping Li and co-workers from the Wang group in Stanford discovered superconductivity in Nickelates. Here is a picture of the graph of their original publication, resistivity versus temperature. For the undoped Nickelates, niobium nickel 02, you have a bad metal behavior at high temperature and a weak insulating behavior at low temperature. But if you dope it with 20% strontium, you get a superconducting transition at 15 Kelvin. For us theoreticians, it's maybe not so surprising because 20 years earlier, Anisimov, Rice, and a co-worker actually discussed that Nickelates are an analog of the cuprates, and therefore we should expect superconductivity in these systems. It's maybe more surprising that it took so long, namely 20 years, to synthesize these materials, and it even took 1 year before the next group, the group of Ariando from Singapore, was able to reproduce these results. Just to recall, for the cuprates, it only was a matter of a few months to recover or to reproduce the results. For the Nickelates, it took 1 year. That shows again how difficult it is to make these systems. And let me also mention that just 2 weeks ago, also lanthanum nickelate was found to be superconducting. So there is a big excitement about that. We have a new class of superconductors, and it's particularly exciting because these systems are on the one hand very similar to the cuprates, but on the other hand also different. And that's maybe something where we can learn more about superconductivity from. What you see here on the left side is the crystal structure of this infinite layer niobium nickel 02. So you have here the nickel square lattice, green atoms, and oxygen 2 in the plane. And these planes are well separated in the infinite layer structure by the niobium atoms. So it's the same crystal structure as the arguably simplest, maybe not the best cuprate superconductor, calcium kappa 02. And it also has the same formal valence. So calcium is 2+, kappa is 2+, niobium is 3+, nickel is 1+. That makes both nickel and kappa is 3d9 formal valence. And that already shows you here how similar it is. And later on, we will also see what the differences are. Because there's so much excitement and so many experimentalists and theoreticians are working on that, you can call it a new age of superconductivity, marking a breakthrough and a big experimental and theoretical efforts like the human ages of Stone Age and Iron Age and Bronze Age. We have here the Copper Age, the Iron Age, and the Nickel Age. As I already explained, the hope is to better understand high TCs because of similarities, but also differences. Because it's quite similar to the cuprates, we might hope to end up at similar TCs as the cuprates on the long run. Maybe we learn enough that the next age of superconductors then is indeed a room temperature superconducting age. Well, if you attended Lilia's talk yesterday, we already have superconductors at room temperatures, namely these hydrates. But they are at a large pressure. They only exist in a diamond anvil cell. They are also conventional phonon-driven superconductors. So it's very important that people like Lilia are studying it and improving it. For those of us who are more interested in correlated systems, the nickelates, iron pnictides, and cuprates are maybe a little bit more fascinating. Okay, now that is where we would like to end up, and that is how the most recent discoveries of the lanthanum nickelates goes to. So you see again, it's difficult to make these systems, and we are even going in the wrong direction with the TC. Here's the outline of my talk. I will start discussing why it's so difficult to make these nickelates and possible problems with the synthesis. So one topic is that you can intercalate topotectic hydrogen or also have excess oxygen in these systems. Then I will discuss the similarities and differences between nickelates and cuprates. So nickelates have many more orbitals. So there's a gamma pocket, a nickel Z² orbital, niobium 4f orbitals. But we did correlated calculations with dynamical mean field theory. And all of these orbitals are there in DFT, but in the superconducting doping regime, I will show you that you can calculate what they do, but they are not important. You can calculate them once and then forget about them. What is not going away is the A pocket. That is important as an electron reservoir. So if you describe the nickel x² minus y² orbital with the Hubbard model, you have to carefully translate the doping because part of the doping is going to the A pocket, but the A pocket and the x² minus y² orbital don't talk to each other. They don't hybridize. And because of that, it is more like a passive, a bystander in a reservoir where you can put holes into. We then also have done beyond DMFT calculations using the dynamical gamma stands for the vertex approximation. And we were even able to calculate the phase diagram before experimentally it was measured. And I will show you that these results are quite good. I'm very happy about that. And I'd like to discuss, if time allows, why for predicting TC good, you need to take into account the vertex dynamics. And our most recent results go into other nickelates, namely going from the infinite layer to a finite layer structure. Okay, that's the outline, and let's start with the synthesis. So why did it take 20 years to make these nickelates? But nickel here is in a +1 electronic configuration in these niobium nickel O2, and that's very difficult to obtain. And the recipe used by the one group, but also used previously by other groups to synthesize other layered structures of other transition metals and also of nickelates, is two-step, and both steps are very difficult. The first step is to use the pulsed laser deposition on a strontium titanate substrate, and you have to deposit not niobium nickel O3, but you already have to deposit the doped system. And there you see already for this doped system, it can be very difficult because part of the strontium can cluster in parts of your surface, and then you don't get the perfect homogeneous doping you want to have. Here you still have a perovskite structure, and these perovskite heterostructures have been proposed by Gignard and also by Philipp Hansmann in his PhD thesis to be also analogons of the cuprates. These are D7 systems, and there you need a particle hole transformation of the EG orbitals to get a perfect analog of the cuprates, and it's very important to make your crystal structure proper. However, the nickelates that have been found to be superconducting are O2 components, so you need another step to reduce from the niobium nickel O3 to the niobium nickel O2. And that is done by using a detergent calcium dihydrate, and with that you get rid of the oxygens here that are in between the layers. You form calcium oxide and water, and you end up with these infinite layer nickelate structure. At least that is the ideal situation to end up. Things are more complicated in experiment, because this reduction with calcium hydrogen 2 might result in different end products. So that's a perovskite to start with, say lanthanum nickel O3, and you want to have this infinite layer structure, but instead you could also have a topotectic hydrogen where before the oxygen was. That has been observed in early transition metal oxides before, actually even in nickelate. So there are some experiments showing that you have some lanthanum nickel O 2 point something hydrogen something. So these systems can occur. And what we have done here last year is a calculation of the binding energy for the hydrogen. So we take this infinite layer structure and calculate the energy we gain to bind the hydrogen. And you see here positive binding energy means the hydride phase is energetically favored. And indeed, we find that for the early transition metals. For the cuprates, on the other hand, it is preferable to have the infinite layer structure. And the nickelates are just at the borderline where it's very balanced. So the undoped compound in blue here is the lanthanum nickel O2, but also the niobium nickel O2. They prefer, energetically at least, to have hydrogen intercalated. But if you dope it with strontium, so the fully strontium nickel O2 in red, but also the 25% doped system, they prefer the infinite layer structure. But that tells you that at least for the lightly doped nickelates, you have to watch out. You have to watch out that there might be hydrogen in the system. And the problem with the hydrogen is you don't see it in standard experiments. So if you do X-ray, the hydrogen is a small atom. You don't see the hydrogen in a standard X-ray procedure, which our experimental colleagues typically do. You do see if you have some excess oxygen, like having instead of two hydrogen atoms here, one oxygen atom, that occurs very often. But these phases can be more easily thrown away if they occur in your synthesis procedure. Why do we bind the hydrogen? It's a simple DFT calculation and it's a simple understanding. So if you have the early transition metal oxides, the vanadium, for example, or titanium, Z-squared orbital, that is the orbital that points in the direction of the hydrogen. It's unoccupied. And then if you put in a hydrogen atom, you form a bonding, anti-bonding pair. And therefore you gain energy. The electron of the hydrogen goes into the bonding pair, and you can even put a second electron from another vanadium d orbital here. So you gain energy. That is why we gain energy here. However, in the late transition metal oxides, these squared orbitals are already occupied. Now, if you bind hydrogen, you have again bonding, anti-bonding, but now you gain some energy and you lose some energy. And for the nickelates, it's pretty much balanced. And for the cuprates, you lose energy in the process. That is the physical understanding behind it. And this has very important consequences. Before, let me just also mention that strain can help to get rid of the hydrogen. The strontium titanate surface has a strain like here, so that is not so good. You will easier have hydrogen in your system, but if you have not a tensile strain, but a compressive strain, you can get rid of the hydrogen. Now, if you have the hydrogen in your system, instead of having the nickelate infinite layer structure, the physics is completely different. So that is our calculation with dynamical mean field theory, with electronic correlations, taking all nickel d orbitals, all lanthanum d orbitals with CRPA calculated Coulomb interactions into account. And you see here the A pocket. You also see it's hardly visible here. That is the x squared minus y squared orbital. Here's a zoom in. There you see the x squared minus y squared orbital. It's so hardly visible because we have a strong mass enhancement of 5, and that means the x squared minus y squared band only carries a fifth of the weight of the other band, and also because of the electron-electron interaction is a little bit more smeared, broadened, and therefore it's hard to see. But we will discuss it later. We have the A pocket and the x squared minus y squared orbital that makes the physics. If you go instead to the nickelate with topotactic hydrogen, you have 1 electron less on nickel, so you have a 3d8 configuration, and then Hund's rule coupling becomes very important. It means you form a spin 1 of your 2 holes you have, and these 2 holes also prefer to occupy different orbitals. Say, so in the calculations, it turned out it's the x squared minus y squared and the z squared orbitals that are occupied. This spin 1, 2 orbital and 3-dimensional electronic structure is very bad for superconductivity. And as you see here, the undoped compound even is a Mott insulator in this case. So that is something you need to consider if you go to the low doped regimes of the nickelates, that you can have this extra oxygen, not discussed here, but it's very similar as this hydride, or you can have topotactic hydrogen in these systems. Okay, the next topic I'd like to discuss is to look into more details in the electronic structure. Of course, we haven't been the first to do that. So with the discovery of the nickelates, there has been a boom of theoretical papers, many DFT works. What you see here is just the DFT band structure of the cuprates and the nickelates. And here in Kappa brown, you see the x squared minus y squared orbital crossing the Fermi level in DFT. But just beneath it, with a very tiny charge transfer splitting, is the oxygen band. And that means if you go beyond DFT and now include electronic correlations, as Zahn and Sawatzki and Anderson have been proposed, you form some Hubbard bands instead. So your x squared minus y squared orbital splits into 2 Hubbard bands, and the first holes go now into the oxygen. So in this situation, because of the electronic correlations, the Hubbard model is actually not the proper model for the cuprates. You should rather consider an Emery model. For the nickelate, the situation is different. The oxygens are way further down in energy. Therefore, your holes will not go to the oxygen orbitals. But instead, you see here at the gamma point and at the A point, for both niobium and lanthanum nickelates, you see some pockets, which you also see here in the Fermi surface. So that is the Fermi surface you also know from the cuprates. And then you have the gamma pocket and the A pocket. And the x squared minus y squared Fermi surface sheet is a little bit warped compared to the cuprates because of these pockets. But otherwise, it's very similar, like that kind of Fermi pocket. Now, you have these 2 pockets, and then you also see here the z squared orbital. That is much closer to the Fermi energy than in the case of the cuprates. So that also has to be taken into account. But this is just a DFT calculation. Many people have done that. Now electronic correlations have to be taken into account. And what I will show you is that you can, in the superconducting doping regime, forget about the gamma pocket, the z squared orbital. The oxygen is anyhow not important, but the A pocket stays there, but it's only a passive bystander. Let's now go through all of these orbitals step by step in proper correlated DMFT calculations. That electronic structure I already have shown you before for the lanthanum compound. For the niobium compound, you see here the gamma pocket, and that's the first one I'd like to talk about. For lanthanum, we find it to be above the Fermi energy because we take into account also the CRPA Coulomb interaction calculated on the lanthanum or niobium sides, and that pushes the gamma pocket up. So in the lanthanum compound, it is not there. In the niobium compound, it is there. It's maybe a little bit too low here in the calculation because for the niobium, you also have the 4F states, that are close to the Fermi level. We know that is wrong. They Hubbard split into bands, into Hubbard bands, and therefore you have to deal with them in DFT plus U or put them in the core. And here they have been put in the core, but then your gamma pocket shifts a little bit too low. So if you have a better treatment of the 4F, it's a little bit higher. But anyhow, as you see here, it doesn't matter. Even if you have them too low to start with, if you dope the system into the superconducting doping regime, they are above the Fermi energy. So for the superconducting doping regime, the gamma pocket is not important. And also for the lanthanum nickelate, it shouldn't be there. Okay, that is the gamma pocket. Next, how about the Z-squared orbital? So we have done here, these are the K-integrated spectra now of DMFT for the niobium and for the nickel d orbitals. And what you see here is the undoped, the 20% doped, and the 30% doped compound. And you see the undoped compound, it's a one-band structure. Only the x squared minus y squared orbital in green goes into the game. If you dope it, the other bands move up, but at 20%, it's still safe to say you have a one-band picture. At 30%, you are just at the crossover regime where the other bands start to come into the game. Let me mention that similar results also have been obtained by Karp, Andy Millis, and others, at least for the undoped compound. We have also done the doping calculations. And there are also some other studies, so there is still some controversy in the literature. And let me just mention one, namely Frank Lechermann, because he did his PhD at the Max-Planck Institute in Stuttgart. So he says that the Z-squared orbital is also relevant and more filled than in these results. But he takes very unrealistic large U interactions and doesn't take the niobium D interaction into account. So that means that up to the superconducting doping regime, also the Z-squared orbital can still be disregarded. If we do the proper calculation, we include it, but we see it's not relevant. So how about the 4F? So here we have calculated the hybridization of the niobium 4F with the x squared minus y squared, which is there to stay. And it's very small, it's 30 millieVs. And you have to take this hybridization squared, you have to divide by u, and then you have to take the exponential to calculate the condo temperature, and it turns out it's 10 to the minus 50. So there will be no condo effect with this niobium 4F. There can be, in the undoped compound around the gamma pocket, some exchange splitting of the gamma pockets. The gamma pocket couples more strongly to the niobium 4F because the gamma pocket is a niobium 3D orbital, and this exchange splitting is interaction driven, not hybridization driven as a condo effect. That can happen, but only for the gamma pocket for the parent compound. Okay, next, how about the A pocket? The A pocket stays there. As you maybe here also see, also for the dope compound, the A pocket is still there. But by symmetry, the hybridization of the A pocket with the other orbital that is in the game, that's the nickel x squared minus y squared orbital, is 0. That means they don't talk to each other. The A pocket, except for maybe some residual Coulomb interaction, is just an electron reservoir, a passive bystander. As I will show you on the next slide, about 50% of the holes go into the A pocket and 50% go into the x squared minus y squared orbital. That means altogether we arrive at the following picture. On the left, you see the cuprates. We have the x squared minus y squared orbital, but we can't forget about the oxygen orbitals. The holes go into the oxygen orbitals, and we need an Emery model. And the Hubbard model might only serve as an effective model in the case of the cuprates. For the nickelate, the oxygen orbitals are further away down, Also, the gamma pocket and the Fs are not really important. So we can live only with the x squared minus y squared orbitals. Of course, the hopping from one nickel side to the next is still mediated by the oxygen, but only virtually. No real holes go to the oxygen. And then here you have the niobium A pocket, that is the niobium XY orbital. And 50% of the holes go here, 50% of the holes go here, but it's on another plane and it is not hybridizing. So it is like an electron reservoir. You only have to properly calculate the doping. Here are actually the orbitals as they come out of a Wannier function projection. That is the orbital going with the A pocket, and that is the orbital going with the gamma pocket. That's the Z squared orbital, which can more strongly hybridize with the nickel Z orbital. Okay, so that is the situation. So we have a one-band Hubbard model plus an electron reservoir. Next thing to do is to really calculate the doping of our Hubbard model, or the occupation of the x squared minus y squared orbital as a function of strontium doping. And that's for lanthanum and niobium nickelate. You see the undoped compound because of the A pocket is a little bit doped in both cases. And then if it's not a perfect line, but as a first approximation, you have a linear dependence. It bends off a little bit for larger dopings, but it's about 50% of the holes go into the A pocket here and 50% go into the x squared minus y squared. So we end up with a one-band Hubbard model description. We can calculate by a Wannier function projection our hopping elements. We can calculate the U for the single band with CRPA. From tons of experience with other materials, we know if you take a static U instead of a dynamic U, which we would have in GW plus DMFT, as advocated, for example, by Antoine, we have to increase this U by about 0.5 eV. That's just experience for tons and tons of transition metal oxide. So instead of the 7T for the U, we get an 8T for the U for this niobium nickel O2. So that are the parameters, and the doping you can read up from this figure, and then you can do calculations with one-band Hubbard models. And indeed, we did so. We now went beyond DMFT, only taking this x squared minus y squared orbital into account, and did the gamma A calculations. That is the Fermi surface at two different temperatures. And here you have the undoped parent compound, which has about 5% holes in the x squared minus y squared orbitals. And here you see a pseudo gap. So the undoped compound has a pseudo gap, and the doping for the superconducting regime is about here, where you don't have a pseudo gap on your Fermi surface. We can then also calculate the superconducting critical temperature. We do that in a simplified d gamma A calculation. So the first step is to calculate a local vertex from an impurity model, then do a ladder in particle hole and transversal particle hole channel that takes into account all the spin fluctuations, also charge fluctuations, but they are not important here. And then we take these spin fluctuations and calculate from that the superconducting coupling vertex in the particle-particle channel, and calculate the particle-particle channel in one run. So it's a poor man's version of a fully fledged Parquet d gamma A, or in a FRG way you would couple these equations. Only the first step. We don't take any feedback from the particle-particle channel to the particle hole and particle hole bar channels into account here. Doing that, we can calculate the superconducting susceptibility. D wave is dominant. You won't be surprised. And you see here the eigenvalue is approaching 1, which means the susceptibility is diverging in the superconducting doping regime. We can then calculate the phase diagram, critical temperature versus strontium doping. as I explained before, we have to carefully use our fully multi-orbital calculations to translate the strontium doping to a doping of this single x squared minus y squared orbital. So it's this 5% for the undoped compound, and then you end up with something like 17% for 20% doping. And that is our result here. That is our TC. And at the time, in February last year, we calculated this phase diagram. There was only one experimental data point for this 20% strontium doping. The TC is a little bit too high. It would have been very simple for us to increase the U. Then TC would go down and we would be on top of the point here. but we think that the way we did it without adjusting parameters, you might argue about this ad hoc enhancement of the U, but that's from experience. We prefer to have it here, and we think there are good physical reasons why it should be a little bit too high. I mean, we are talking here about 15 Kelvin. That's tremendously good for so difficult to calculate quantity as TC without adjusting any parameters. And we think it's higher because this feedback of the particle-particle channel, if these fluctuations get larger, we think they will suppress the antiferromagnetic fluctuation in the particle-hole channel. And therefore, in the theoretical calculation, if we improve our method, we will go down a little bit. On the other hand, in experiment, you can also have all kinds of disorder effects, for example, that are known to reduce the TC. Okay, that was our calculation, and then one month later, the one group and also the Ariando group, they measured the phase diagram, and it's that one. And considering that we overestimated TC from the beginning, I think that's a very good prediction of the TC. In the cuprate, in the nickelates, if we had adjusted the U, as I mentioned before, for a larger U, that point would have been here, and we would have been on top of the experiment. Still, I think that is an error cancellation. The U is not so much bigger than we have found here. And let me mention here the importance of this blue background also. That is the regime where you can trust the one-band Hubbard model. For small dopings, at least for the niobium compound, you should expect the gamma pocket. For larger dopings, you should expect instead z-squared orbitals to play a role. Of course, here this transition we can't precisely predict. Yeah, there is some uncertainty in the method. It can be a little bit more here or a little bit more there. But we know for somewhat larger dopings, these squared orbitals come into the game, and for smaller dopings, also the gamma pocket may play a role. Okay, so that was quite exciting. We have calculated TC. Let me just explain to you why the TC is rather low. So if you do a RPA calculation and many other calculations, you would end up with TCs that is not 40 Kelvin, but 500 or 1000 Kelvin, way too high. And the reason for that is the vertex dynamics, which we take properly into account in D gamma A. So our starting point is a local vertex with a full frequency dependence taken into account. That is shown here. So you have here the two frequencies. The third bosonic frequency is set to 0. From this local vertex, then calculate in a beta ladder the full vertex or the antiferromagnetic spin fluctuations, and from that you get the superconducting pairing vertex. And you see here the vertex is suppressed for small interactions, and the superconducting pairing interaction is suppressed for small interactions. In a RPA or recoupling approaches, you would not have this suppression. You would have a constant vertex. Indeed, the constant background here is just minus u of the vertex. But if you take the minus u, you effectively do an RPA calculation, and you get a way too large lambda. You get TCs that are in order of magnitude too high. Then you can increase the amount of frequencies you take into account. So this suppression here also then you end up with this lambda and lower temperatures, or you take the full frequency dynamics into account, and then you end up with a reasonable, very good estimate of TC. So the next question to ask is, why is the vertex suppressed here?
Karsten, you have five more minutes of talking time.
Okay, thank you. That is the full vertex in a little bit other color scales. Now I've used subtracted. You can do the Bayer, you can have second order, third order perturbation theory already describes it pretty well. But you see the suppression here, you can already describe in second order. In second order with this particle-particle contribution. And what this particle-particle contribution is doing, if you calculate the antiferromagnetic spin fluctuation, as you know, you have this RPA ladder, you have a U, a chi0, a U, and this kind of diagram with two particles here just has a particle line instead of a whole line, and therefore it has the opposite sign, and that suppresses your vertex. And as you see here, for the frequencies, nu plus nu prime have to be 0. And that is why you get this side diagonal where you have the strong suppression. And this way, with this dynamics, even on the local level, calculating this coupling vertex in an impurity model, you can already describe this very suppression. And that's also why we think that then if particle-particle diagrams become more important, or the non-local contributions, if we approach the superconducting regime, that this will go in the same direction and somewhat suppress superconductivity. Okay, just as my time is running out, we also have looked at layered nickelate compounds. So you can start with this Rudolph Popper phase and do the same calcium dihydride reduction to get bilayer structures here. This T prime type is more stable. You can also have topotactic hydrogen here in black in this structure. It's a very similar story as for the infinite layer compound. Topotactic hydrogen makes your electronic structure very, very different. It's also a Mott insulator. And if you calculate the TC, you get very similar critical temperatures as for the infinite layer structure. So these already have been started to synthesize experimentally, but doped systems with superconductivity still have to be found. Okay, here I come then to my conclusion. The first step regarding the synthesis, so you have to watch out for extra hydrogen or extra oxygen. That is easy to detect in experiment. That isn't. You're blind to that if you do standard experimental procedures. And that changes your electronic structure very much, and you won't get a superconductor. In particular, for low dope system, that is very relevant. Then I've shown you that for the nickelates, you can effectively describe them by a one-band Hubbard model for the nickel x squared minus y squared orbital. The A pocket is just an electron reservoir, a passive bystander that comes out from DMFT calculations with multi-orbitals taken into account. And then as a next step, at least in the blue region of doping, you are good with a one-band Hubbard model. We calculated the phase diagram, and the TC is very good compared to experiment, even though we did the calculation before experiment. And the reason why the TC is in such a D gamma A calculation reasonably low is that particle-particle contributions reduce already your local vertex, and with this your antiferromagnetic spin fluctuations and your glue for superconductivity. There is still a lot to be done. There are coming tons of experiments, or the RIX experiments now out, and I'm very sure that these nickelates will be one of the hot topics of condensed matter physics in the next years to come. Thank you very much.